This is Lab 14, where we're going to talk about LASSO primarily. And this is associated with Lecture 14, where we talked about LASSO also. And, whoops, I got those backwards there. What's going on there? Strange. Well, ain't that strange. Let's see if I can get this correctly. There we go. And we're going to work with this TED Talks data set again. So our TED Talks data set has this variable views. We're trying to predict views from word feature data and the description of the TED Talk. And last time we had used this package glmnet. So we can load that up again. And then there's also this package glmnet utils, which you can install, which has a nicer interface for glmnet. It's going to have the kind of traditional formula interface that we're used to for LM and some of the other packages. So we can load that one up, and it's gonna give us new versions of CV, glmnet, and glmnet. So if we want to fit a LASSO model, we should first just look real quick at the glmnet package information. And in particular, last time we had used this parameter alpha, and alpha is the elastic net mixing parameter. So here is our penalization. It's 1 minus alpha over 2, it doesn't really matter, times the 2 norm penalty squared plus alpha times the 1 norm penalty. And so it says here alpha is 1 is the LASSO, and alpha is 0 gives us ridge. And so that's pretty much exactly what we're talking about class. I guess they have about 1/2 in that too. Not a huge deal. There's also that parameter lambda that we can pass in, which specifies the lambda or the sequence of lambdas that we want to try. So in this case, if we're going to fit purely a LASSO model, we're going to specify alpha as 1. And here we're using this interface glmnet utils package, where I use my kind of traditional formula interface. So I want to pick log views from my other covariates. Family is Gaussian. Alpha is 1 for LASSO, and my data is this data frame I created above with my views variable and my other features, my other word features. So I can fit this pretty fast, nicer interface. And I could look at, say, the betas from this LASSO model. And again, so this, I guess, it's 433 rows and 81 columns. And the 81 columns are, I guess there are, we can check real quick if we look at our LASSO model lambda. Of course, this is not going to be giving me what I want, right? Yeah, so there are 81 lambdas, right? So that's why there are 81 columns here. You notice there's a bunch of dots here. The dots, and this is not a matrix, but a DGC matrix. Basically, it's a sparse matrix. All these dots mean zeros. The point with LASSO is that it's zeroing out these betas and therefore doing some kind of variable selection. So the dots just mean zeros, and then we see the actual numbers where they're non-zero. And you could convert this, and it's useful to know that you could just always call as.matrix to get the normal matrix version, but you're just going to see a bunch of zeros, and so the efficient way to store this is not to store these bunch of zeros, is to use a more efficient data structure to store those, and so that's what's going on there. We can of course plot our beta values for our whatever 433 variables for each line against the lambda coefficient here, and we see kind of a similar picture to what we saw in ridge regression, but now we see some of these just plummet in towards 0, and they as we increase lambda, as we penalize things more, these things really kind of careen into 0, and in fact will eventually become exactly 0. So this is the difference in character if you compare this to a ridge regression model. The ridge regression model, we didn't get these kind of exactly equal to 0. They kind of smoothly squished towards 0. And these, they kind of very quickly just absolutely zero out. And that's why we get so many zeros in this matrix, is because we're actually zeroing things out with this L1 penalty. So that is, that's all good. But I guess we could look at, if we look at the similar model, right? If we could look at a ridge model, let's just look at that real quick. Right, so all I'm going to do here is change alpha from 1 to 0. That gives me our ridge model. And I could, instead, here, I could plot my LASSO model, our ridge model. And you see how they kind of smoothly squish in towards 0. And as opposed to in our LASSO model where they very quickly kind of zero themselves out. So that's cool. We still have, for our LASSO model, we have this parameter lambda, which ultimately we'd actually need to choose, right? And the way we do it was with some cross-validation. And so let's see, what's my sequence? Let's say lamb sequence is, let's just say it goes, just look at powers of 10. Typically you want these things to span multiple orders of magnitude. So let's say it goes -10 to 10, and let's say we get 100 of these. That's my lambda sequence, something like that. And let's say LASSO CV is glmnet, or what's it called? It's called cv.glmnet. And I can specify sequence of lambdas over which to search, and I can run that, and that's going to fit my, it's going to do a cross-validated fit, and it's going to give me some errors, which I'm not too concerned about. But that's my cross-validated, and we should be able to plot this. LASSO.cv. And let's actually get a little bit more resolution, because it's going to be more interesting. So it looks like the interestingness is going on. Not really above 0, but -10 to 0. Not sure why it shows all the way to -20. Because surely if I look at LASSO.cv, the minimum value of this should be 1 to the -10. I guess this is log base E and not log base 10. In any case, it looks like the interesting stuff is going on here. Let's actually just narrow this range of potential lambdas a bit. So let's just go to 0, and let's just say -5, something like that. So we'll keep 100 of these, we'll refit this. And once that's fit, we'll make our little plot again. Let's see if we can get this interesting. Okay, so this is kind of just zooming in on this, and we have this nice, cool little plot. And you can see we're getting a cross-validated MSE, which says that somewhere about here, about e to the -3 or a -4 point something, is going to give us kind of the optimal lambda. You notice at the top here, there are these different numbers. These are the number of non-zero coefficients. So it looks like, right, so if you have very little penalization, very small lambda, you basically have all of your covariates, 423. As I increase my penalization, I start to get fewer and fewer covariates. If you penalize enough, you get 0 covariates. It's just going to be an intercept model. It's just going to predict everything as y bar. And you see it flattens off there. So it looks like between 100 and 200 covariates is the best thing to do. So we could get LASSO.cv, we can get our minimum lambda, So best lam is that. Something like that. So it looks to be about 0.01. And I get my best lasso model. I can now grab this best cross-validated lambda there accordingly. And I can fit this model. So let's just fit this, but instead of passing in the whole sequence of lambdas, let's just pass in best lam, and that will fit using that best lambda value. That'll fit my best model, best lasso beta. Lasso. All right, so this should now only has one column and it has 433 variables because we've only passed in our one best lambda. And if you look at this, here are the coefficients associated with our kind of best model. And we could, for example, which one of these are non-zero? About 169. So apparently this looks between 125 and 262 here, and it turns out our best model is at about 169, and you can actually get the cross-validated error. I should be able to get that. And you can, I'm sure you can get it from, let's say, you should be able to get that cross-validated error out of here. In any case, you can use your best fit model. I can predict using it. Let's say, well, it doesn't like my data for some reason. There we go. Okay. So let's just do a little plot here. Of course, this is kind of all on the training data, where I plot true views against the predicted ones here. So it does okay. It's a very hard problem, so it's not doing amazing, but it's doing okay. We can also, in the last couple of minutes here, we can also look at the elastic net model. And the elastic net is kind of really similar to all of these. Let's just let's grab our code here. So elastic net is a combination of lasso and ridge, and I could say put alpha at 0.5. That would be going to be half ridge, half lasso, and fit this thing, and we can make our nice little plot here, and hopefully what we'll see is something nice and interesting here. So we want to plot the lambdas against the betas. And it kind of has a in-between behavior. Some of these things get directly sent into 0 real quick, and some of them kind of more smoothly. So it has kind of a trade-off. If I put it, much closer to 0, it's going to behave more like a, 0 should be ridge regression. So if I pump this alpha down close to 0, it's going to behave kind of like ridge regression, something like that. But if I bump it up close to 1, it's going to behave something like lasso. And in between, it will have kind of in-between characteristics of these things. So one can get both variable selection and can get some kind of dealing with collinearity problems. And all the other stuff we talked about here kind of applies, all of the prediction and all those other cross-validation functions. So this is kind of what it looks like. So doing a fair amount of variable selection because it has that L1 penalty. if I pump down that alpha, I should get less variable selection. It's a little bit hard to read from this. But that's kind of a real quick primer on LASSO, which does this variable selection on elastic net, and kind of on the connection to ridge and how all that works together. So I will stop here